I didn't actually mean to stop recording that time, but oh well, it'll make the video faster to upload. Anyways, so we have 5 shapes in the D sublevel. What's interesting too is that each one of these shapes that we have found, so the S has 1 shape, P has 3 shapes, D has 5 shapes, and the F has 7, right? So 1, 2, 3, 4, 5, 6, 7. Okay, each one of these shapes contains 2 electrons total. So the S orbital has a total of 2 electrons in it. P has 3 shapes, each containing 2 electrons, so the P orbital can have 6 electrons. I can have 2 electrons in each one of my D orbitals, which means that I can have a total of 10 electrons. For the F orbitals, we can have 2 in each one of these shapes. They're randomly moving around all the time, so we can't really say like where exactly they are in space, but we do know that there's 2 in each one of them if the F is full. And so this would be 2 electrons per shape times 7 shapes. We get 14 electrons can fit in the F shape. Now what's interesting about that is that the periodic table also reflects this. So the periodic table was invented way before we knew anything about electrons. So this is really interesting. Group 1 and Group 2 are in what we call the S block, and we said that the S block has 1 shape. So the S block has 1 shape times 2 electrons, so we can fit 2 electrons in each energy level for the S. And it turns out like here, you got 1 box, 2 boxes. There's your 2 electrons. In the periodic table, there's 2 boxes in groups 1 and 2. So this is the S block. And that's how many you can fit. The P block has 1, 2, oh, my dots aren't showing up. 1, 2, 3, 4, 5, 6. So the P block has 3 shapes times 2 electrons each, so you can fit 6 electrons at each energy level for the P shapes. The D has 10. Okay, so 10 electrons for the Ds. And the F block, so I'm not going to count them, but the F is 14, just like we figured out before. Now, what's also important to know is that as the period increases, that means that the energy level is increasing. So we have lowest energy at the top and highest energy at the bottom. Okay, so as we increase the period, energy goes up. We always want to write our electron configurations from lowest energy to highest energy. Okay, so what is the maximum number of electrons that can fit in a 5D orbital? We said D orbitals have 5 shapes. Here, when we say 5D, that means the energy level is 5, but because it's D, we conclude that that means 5 shapes, and each shape can have 2 electrons, so therefore there's 10 electrons in the 5D shape. This one's tricky. What is the maximum number of electrons that can occupy an n equals 3 sublevel? So we go back here and we find, we're going to try to find where n equals 3, okay? And so that's period number 3, which is this one. Let me make this a different color so we can remember what we're looking at here. Okay, so n equals 3 is this one. And so you see we have those 2 electrons, and we have these 6 electrons in the P, but we also have a third energy level here, which is 10 more electrons. So to answer this question, we have 2 in the S, 6 in the P, and 10 in the D block. So you end up with 18 electrons. So D is our answer here. Now, there's a short way to record electron configurations. When we say the word configuration, what we really mean is, where is the electron? Or really, where are electrons? Because most atoms, everything except hydrogen, have more than 1 electron around. So, every time we do an electron configuration, there's some rules we have to follow. There can only be 2 electrons in any one shape. One of them has to point up and the other one points down. That's because 2 pieces of matter, which electrons are matter, They have mass, even though it's very, very small. Two pieces of matter cannot be identical. They cannot have the same energy level, be in the same place, and spin in the same way. We also want to follow the rule that we fill the lowest energy first, and we want to list the orbitals in order of increasing energy. The notation we use is like this. The black here represents the energy level, which is the same thing as the period. Mostly. I'm going to show you in just a second that changes a little bit when we get to the D and the F block. The red represents the shape of the orbitals, which is also kind of buried on the periodic table. We had them labeled on the last side as the S block, the P block, the D block, and the F block. Then finally, our last quantity here is going to be the superscript, which represents the number of electrons in that particular energy level. So let me show you how this works. So first off, we have hydrogen, which is right here. Okay, so hydrogen's in the upper left corner of your periodic table. It is in period 1, so you would say energy level 1, and this is the S block, so it's in 1s, and it's the first box, the first element, so we're going to write 1s1 for the electron configuration. That's the simplest element that there is. It's just one electron in the lowest energy level possible. Oxygen is a little farther down the periodic table, so here it is right here. It's in group 2. Everything before oxygen is still there, so we always start at hydrogen, and that is always a 1s because it's in the S block. We get there, we got to sort of play chutes and ladders, so we got one spot there, one spot there. That means I got 2 electrons in the 1s energy level. And then we jump down to period 2 with lithium, and we're in 2s now, and I got 2 spots there, so I write 2s2. Then we jump across here, and we got 1, 2, 3, 4 spots to get to oxygen, so I'm going to write 2, and it's in the P block, and I'm going to put 4 electrons in there. Now I can double check my work because oxygen is element number 8, so that means it ought to have 8 protons and 8 electrons. So this should add up to 8. So 2 plus 2 is 4, plus 4 more is 8. So cool, we did that right. All right, now sulfur. Sulfur is interesting because I'm going to try to erase these extra drawings here. There we go. Sulfur is interesting because it's a little bit farther on. It's in the same group as oxygen is, but it's farther down the periodic table, so it's a bigger atom, so there's sulfur. So we're going to start back at the beginning again, and so the beginning is 1, principal quantum number 1, and in the S block, and we got 2 electrons there. Then we jump down to 2, and it's 2s2, and then we jump across here for those 2p block, and there's going to be 1, 2, 3, 4, 5, 6 of those. That's totally filled up because we are still not at our final point, sulfur. And then down here 3s, I'm going to have to write over this, but that's okay. 3s1, 2 of those, and then I jump across and I'm in 3p now. And we got 1, 2, 3, 4, 3p4. So that's the final electron configuration for sulfur. Iron is in the middle of the D block. So what I gotta do there, it's kind of the same process. It's kind of the same process, but my iron is in the middle right here. So let's see what we get there. I'm going to write the configuration up at the top here because I kind of ran over it on the other spot. But we start back in the beginning, so we got 1s2, and then 2s2, and then 2p, that's 6, and then 3s2, I'm going to have to jump down here on the next line, and 3p6, and then 4s2, and then here, this one, underneath the circle that I just drew, it says this is the 3D. So what's interesting is once we get to the D's, they drop down an energy level. So I'm going to write 3D, and then I got to count. 1, 2, 3, 4, 5, 6. So 3D6. This entire thing, this is the electron configuration for iron. So you can see as we go down the periodic table, they get longer and longer. You're adding layers of more and more electrons as we go down the table. Oh, also, the F block kind of exists here in between, kind of in the middle of the D block. And when we get to it, so period 6 belongs right here, and period 7 is this one. Oh, that's a terrible choice of color. Let's try black. Okay, so here's this one, and that goes to here. So when we start off in period 6 here, we're at 6s, and then the F block is actually 2 down, and so it goes 6s, and then 4f, and then we go back up to 5d, and then back over here to 6p. So it's kind of a chutes and ladders thing, okay? And you got to keep track of whether you're in the D block or the S block or the P block or the F block. The D block is 1 less than the period number. So this is period 4, so it would be 4 minus 1, so this is the 3D block. This goes in period 6, so you get 6 minus 2, and that's where 4F comes from. Okay, so these are actually going to be on Top Hat as questions to get credit for the lecture material. Write me the complete electron configuration of nitrogen, and then do the same thing for chromium. And then the other type of question we can get is if I give you the electron configuration, you should be able to tell me what the element is, okay? And then finally, look at how many 3D electrons nickel has, okay? While you're doing your online test, you're welcome to use this figure, but remember that we have a final exam where you're not going to be allowed to have that figure. All you have is the regular periodic table, so you do need to learn where the S, the P, the D, the F, all of those things are at. Okay, so naturally, since as we go down the periodic table, it becomes really kind of tedious to continuously write the entire thing out, we had to develop a shorthand way of doing it. It turns out that we do that by counting only the outside electrons, only the outer electrons. Anything that's in the core electrons gets kind of summarized with this shorthand notation. And so we consider the core of an element to be the nearest noble gas before it. Okay, so we're going to go back to this periodic table here. So let's go back to the other. I like it better. So what we have going on here is that as we go down the periodic table, you're adding layers of electrons, but only the very outermost electrons can react. So here is their noble gases, and they are very stable. We call them noble gases just because they don't react. That means that they are sort of paired up and everybody is happy. So if I were trying to find the electron configuration, say for this element number, it's in group 7, period 4. What I would do is start at that point and then kind of backtrack all the way to this noble gas, and that would be the core. Okay? So, oops, too far. For example, chlorine is element number 17. If we pull out our periodic table, look at element number 17 and trace backwards, you'll find that the nearest noble gas core is neon. That means that all the electrons in neon are also in chlorine. But chlorine has a few extra. So if we start at neon and trace it forward again, we'll see which ones are on the outside, and we'll get this 3s2, 3p5. So if I want to write the shorthand configuration, I would use neon in brackets to represent the core, and then 3s2, 3p5 to represent the outer or valence electrons.